All right, friends and neighbors, welcome back to another networking video. We are working through our first chapter in volume 2. So we're going to start with TCP/IP transport layer and applications. Now there's a lot in this chapter. So in the show notes, I'm going to point to a whole bunch of videos that will help you with individual points on this if you want to go a little bit deeper. But for right now, we're going to cover what's in the chapter. So we'll see that the key topics in this chapter, they cover a lot of ground. I will try to hit the high points of each, but you're going to do a little bit of reading on this one or look at some other videos. The exam section is network fundamentals. And as I said, we're moving up to layer 4 now. And so that's TCP and UDP. So there's be some comparison there. And we want to get a handle on what goes on at the transport layer. And then we'll talk a little bit about IP services. At the end of the chapter, we'll talk a little bit about DNS. And then, of course, we'll do the do I know this already questions in the chapter. Now, the top part here is just a quote that I got out of the chapter. The CCNA exam focuses mainly on functions at the lower layers of the TCP/IP model. So that's what happens with switches and routers, right? Layer 2 and layer 3. Layer 1 is the physical layer. We want to know a little bit about that. But we don't affect that to a large extent. So layer 2 and layer 3, but when we're doing security or when we're dealing with network address translation or when we're trying to understand application data flow, we got to understand what's going on at layer 4, the transport layer. So this is not quite as big a focus there. So our key topics here, we're going to look at the functions of TCP and UDP. They're both at layer 4, but they do different things. And then we'll talk about the kinds of port numbers that are out there, and especially the well-known port numbers which servers listen to. And then we'll talk a little bit about an example of a TCP connection establishment. I'll go through some handshakes with you. Connection-oriented versus connection-less. This is the famous definition that we have at layer 4 and comparing TCP and UDP. A little bit about DNS name resolution. And then we'll talk about the header fields that we see in applications. Okay, so first up, TCP has really two protocols. So we call it the TCP/IP model, but you could easily call it the UDP/IP model as well. So TCP and UDP both operate at layer 4. And while we're at it, a lot of folks start talking about the OSI model, right? And so the OSI model is a 7-layer model. The TCP/IP model is a 5-layer model. But OSI is what we call the reference model. There are not a lot of OSI protocols that are out there that people use on a regular basis. We much more favor the protocols that are in the TCP/IP model. But both models call layer 4 the transport layer, and both of them have the same functions at layer 4. Most notably, things like error recovery, flow control, and then multiplexing via ports. Now, most of that is the responsibility of TCP. We'll talk a little bit about UDP, but UDP doesn't have a whole lot going on. Very simple header. It's really to wrap up the data and to give us this ability to multiplex via ports. But TCP handles a lot of stuff. Now, we use UDP for a lot of things, right? When we have short conversations or when we don't want to do error control or things like that. So anything that's real time, and the best example is voice over IP, is going to use UDP. But UDP is often used for our service protocols too, like DNS and DHCP. Now, before we dive too deep into this, a really, really important idea is client server. So if you have a handle on client server, then your life will be easier when you're talking about what goes on at layer 4. When we write a protocol, when we write an application, it's written with a protocol in mind. So this application is going to be either TCP or UDP. Now, all connections in the internet, all of them, can be uniquely identified by 4 numbers. And those 4 numbers are the source and destination IP address and the source and destination port numbers. Those 4 numbers together, there's no way, unless you really work hard at it, to duplicate those between TCP or UDP connections. So they uniquely identify a connection. Those numbers, combined with whether or not it's TCP or UDP, constitute the socket. Now, server applications listen on what we call the well-known ports. So every time you do FTP, or every time you do web, or every time you do mail that's SMTP based, then you're going to go to a particular port. The destination port will be the same for all of the applications that you use. So that's a well-known port. So it doesn't matter if you use Chrome or Firefox or Edge. When you go to a web server that's running HTTP, you'll hit port 80. Your client side will generate a random port. And then you're going to a machine that's sitting on an IP address, and you have your IP address. Those 4 numbers are your socket. So that's a really important idea to remember. Now, the original TCP RFC was RFC 793, and today a lot of the adjustments to TCP, the additions to TCP have been added up into RFC 9293. Now, I call TCP the mother hen protocol because it's very concerned with connections. Are you ready to start? I'm ready to start. Okay, let's start. Let's set up our numbers for this connection. Also, when we get all the way to the end of the conversation, TCP says, are you ready to be done? Because I'm ready to be done. You're ready to be done? Okay, cool, let's be done. So very, very, very concerned about this. Now, TCP also does error recovery. If you miss bytes in a TCP connection, you can ask for them to be retransmitted, or they'll automatically be retransmitted when a timer expires. Flow control, TCP has this thing called the window size. Now, this image that I have here, this is the ASCII art from RFC 793. And if you take a look here, we've got the source and destination port. Now remember, this whole thing is wrapped up in maybe an Ethernet frame, which encapsulates the IP packet, and the IP packet has this TCP header along with the application data. And if we look here, there's some very, very important things to realize. Here are our flags field, here's our sequence and acknowledgement numbers, and here's our window size. Now those 3 things alone handle the data, right? We're going to keep track of the data sequencing, and we're going to keep track of data loss. The window size is what we call our flow control. You're only allowed to send so much data. And then we've got all of our flags that tell us what's going on with this particular part of the conversation. Both TCP and UDP have this source and destination port numbers. Now, source and destination port numbers allow us to do multiplexing. Every application on your machine has a port number to which it is going. And so this is what allows us to multiplex, because you can have multiple connections at the same time. So these are all parts of TCP. Almost none of this is part of UDP, with the exception of multiplexing ports. Now here's an actual packet, and here we can see the source and destination port numbers. There's our source and destination IP addresses. Those 4 numbers constitute our socket. We might also say that, well, it's TCP, we'll make that part of the socket as well, but those 4 numbers are the ones that we're concerned about. Here's our sequence and acknowledgement numbers. Here are our flags that tell us what's going on, and here is the window size, how many bytes we're allowed to send or receive. So this is an important part to realize, that you can look at this stuff all in Wireshark or TCP dump. Some of it you can even see really well in Packet Tracer. We will revisit this packet, and we'll take a look at an example of some of the packet flow in this video. Now, multiplexing is sometimes hard to wrap your head around, but we'll start this way, right? I'm on this machine right now, and on this machine, I can open up a lot of applications. And so the question is, how do I keep track of all of those data streams? In fact, I could open up a single browser, right? I could open up Chrome or Firefox and have multiple tabs going to different websites. How does all of that data to the different websites go to the right tab? And even worse, I could open up the same tab to all the same destinations and have different things on the same website in each one of the tabs. How do I keep track of all that stuff? Well, the answer is that even if I was going to the same destination IP address and the same destination port number, and I'm using the same IP address, all of the individual tabs, all of the individual applications I have running would have their own dynamically generated source port. And that's the difference between the connections. So those client server sockets for each one of my applications, for each one of my tabs, would be how I separate all of those data streams. And those are what we call the multiplexing, or that's how we describe the multiplexing. So even though this machine has the same MAC address, one IP address, I have the ability to separate things, but the thing that allows me to do that is the transport layer. Now, port assignments. You remember IANA, the Internet Assigned Number Authority? Well, it turns out they're not just in charge of IPv4 or IPv6 addresses, they keep track of all the port numbers as well. Now, if you want to read about all of this, you can look at RFC 6335. And this link right here will take you to where all of these assignments are. I'll try to remember to put that in the show notes as well. But we basically have three ranges of port numbers that we worry about. The first one is called the system ports, or the well-known ports. These are the ones that servers listen on. So if you're going to a web server, it's going to be port 80. If it's a secure web server, it's going to be port 443. No matter what you do, no matter what kind of browser, no matter what kind of source you use to go to that web server, you're going to answer, or you're going to request information on that particular port. Why? That's so that servers don't have to try and figure out what you're trying to do. You will always use that destination port. But what do you use on your end? Well, we have the user ports and the dynamic or private ports. And these are what we use on the client side. So we dynamically pick one of these, and then we use that to communicate from the client side. So I'll mention this example. We'll go over it a little bit more later on. But if I am going to a web server, I have my IP address and the destination IP address for the server. Now, how you get that IP address, that's a different story. But my source IP address and the server's destination IP address, the server's well-known port number, and my dynamically generated changing. It doesn't change over the course of the connection, but if I spin up another connection, I'll dynamically generate another one. So all of these dynamic ports on my side to uniquely identify the connection. So those are our three ranges. Now, there are a whole bunch of services that we use on a regular basis. On the TCP side, we have HTTP, and sometimes DNS will be on the TCP side as well. Usually, DNS will be UDP. FTP, the control and data ports, SSH, Telnet, Simple Mail Transfer Protocol, SSL, they're all on the TCP side. DNS and DHCP are typically going to be on the UDP side. TFTP, Network Time Protocol, Simple Network Management Protocol, all on the UDP side. That's because these are short conversations and we're not sending long streams of data. Now, we're going to spend a lot more time talking about TCP in this video than we do UDP because UDP is very simple. It's a very short RFC to read. So if we're trying to understand TCP, what we want to do is look at how do TCP connections start. And they all start the same way, with a three-way handshake. So we're going to do a whole bunch of things during the handshake. We're going to do the SYN-ACK exchange. Now, what are we talking about? Well, I showed you those flags earlier. These identifiers, the SYN and ACK, and then the SYN again, and then the ACK, these are actually just one-bit flags in the TCP header that tell the two sides what's going on with this particular connection. It's a way to synchronize the two sides. So the three-way handshake, the client sends a TCP packet with the SYN flag set. The server responds with its own SYN flag and acknowledgement flag. And then the client comes back with a TCP packet with the ACK flag set. That's the handshake. Now, the sequence numbers are an important part of the handshake and the window size. So both sides are going to determine what their sequence numbers are going to be. And then the opposite side will use those as the acknowledgement numbers. And then we're going to set the window size as well. Now, one important detail here is that when I acknowledge something for you, I'm going to use your sequence numbers, but it's going to be incremented by 1, meaning that I got everything before, and I'm expecting this next byte. So again, the purpose of the handshake is to negotiate the starting sequence number. So in addition to saying, hey, are you ready? I'm ready, let's go, it is the sequence numbers that are a big part of that. And then we set the window size. Now the window size is how much data I'm willing to receive from you. Both sides have a window size. In TCP conversation, each packet has a sequence number, and after the startup, each packet also has an acknowledgement number. And the acknowledgement number is telling you, here's the data that I received from you, meaning that I got it and I was able to process it and everything's good. And when I acknowledge it, I send you an acknowledgement number plus 1 of your sequence number, meaning that I got your sequence numbers that you sent me. Here's the next thing that I expect. So we say sometimes that ACKs are piggybacked on data packets. So if I send you something, I send you my sequence number. Here's my bytes that I'm sending your way. By the way, here's the acknowledgement number that I'm using for you, meaning that here's the last thing that I got from you, or I'm acknowledging what you sent. And if there's no data, I can send TCP packets with just the ACK flag set. It's the same value as the previous packets because I haven't received anything else from you. Now here is an example of the startup handshake. So this slide has 2 things on it. One has the startup handshake. So we'll start here in the upper left, sort of, what is it, and over one of the sides. Anyway, so here's our source and destination port numbers, but here are our flags. So this is, now we got to pay attention to the direction. So here is the destination port. It is a well-known port, port 80, and 1050 is above the system ports or above the well-known port. So that's how we know it's a client side. And the client is also setting the SYN flag. Now the server comes back and says, okay, I see you want to connect. I'm going to send you my TCP packet. Note that the port numbers have flopped, and I've got a TCP packet with the SYN flag set and an ACK set. So this is the SYN ACK from the server, and then the client comes back and says, all right, I'm going to acknowledge you. Here's my flag. Again, the port numbers have flopped. Now the other thing that's happening here is that notice we have a sequence number here, and then we can have the sequenced acknowledgement numbers. The acknowledgement numbers are saying I'm referencing your sequence number here, and it is 1 more than what you sent me. So this is the server saying, I got what you sent me. Here's the next thing that I expect. By the way, here's my sequence number. So the client comes back and says, here is my next sequence number. By the way, I'm acknowledging what you sent me. Now I'll make this point too. You can see that it says relative sequence numbers. Sequence numbers are actually much larger and much harder to work with, so Wireshark gives us relative sequence number, meaning that we start counting at 0 for this particular connection. But actual sequence numbers are much harder to deal with. We can deal with hexadecimal or base 10 numbers. I'll show you an example here in a minute. Now, above me, we've got this right here. This is the teardown handshake, where both sides say, I want to be done. So one side sends a TCP packet with the FIN flag set. That gets acknowledged, and then we see the other side here, in this case, the server, saying, I want to be done too. Here is my TCP packet with the FIN flag set, and then this is acknowledged by the client. So there we go. There's our startup and teardown handshakes. So a little bit more about sequence numbers. Sequence numbers keep track of the data or the bytes that are sent. So the numbers that we're talking about are byte counts. And what I do is I send you data. Now, at the handshake, that's where we both say, here's my sequence number and here's my sequence number, right? The two sides determine that. And the acknowledgement numbers are the same values as the other side is using, meaning that you're referencing their sequence numbers. Now, the reason I keep track of this is because if data is lost along the way, you can acknowledge data from me, and by omitting certain acknowledgement numbers, you can tell me I didn't get that data. And so What I will do is I will keep track of what you're acknowledging, and if you've missed something, I can send it again to you. So this is the retransmission capability of TCP. So what we're seeing here is not only keeping track of the data and ordering the data, because the sequence numbers count up, what we have the ability to do is error recovery or problem recovery, right? If data is lost, we can now return it. Now, the last note that I'll make here is that a single ACK can acknowledge receipt of a lot of data. So you could send me a series of packets, and with a single packet with an acknowledgement number, I can say, yep, I got all the data. So let's say you send me 1,000 bytes, and you send me another 1,000 bytes, and you send me another 1,000 bytes. So you've sent me 3,000 bytes. I send you one TCP packet with the ACK flag set and an acknowledgement number of 3001. And what that means is that I got all those 3000 bytes. The next thing I expect from you is sequence number 3001. Now, if I send you an acknowledgement number of 2001, that means that I didn't get the last 1000 bytes or that I wasn't able to process it. Now, TCP is able to send a continuous stream of octets, but there's a limit. That's the window size. So when I go to a web server, right, you notice that when you go to a web page, there's a lot of data that comes down to you, right? A whole bunch. So that means that the server can say, here's all this data, right? Right at you. And because it's sending me the sequence numbers along with that, I understand whether or not I've gotten all of the data, whether it's all in order. But of course, if I didn't get something, right, because of a delay or because there was an actual error out there, then I have the ability to tell the server what I did and did not get. Now, each segment, each chunk of data has a timer associated with it. The server knows what it sent me, and the server keeps track of whether or not it's been acknowledged. The server keeps track of my window size. So the server knows I sent this data, I'm waiting for acknowledgments, and I'm keeping a timer on all of the data that I sent. And I know whether or not I've overrun the client, whether or not I've sent the client too much. So if I get an acknowledgement that does not contain all or doesn't acknowledge all the data that's been sent, the server knows after the timer expires to send the data that is missing, retransmit it. Now here's an example. Now this is straight up IP addresses here. There's no DNS conversation in this one, hint, hint, wink, wink. But right up here at the beginning, right, packets 2, 3, and 4, we can see that I've done a SYN, SYNAC, ACK conversation. This is the handshake. And then right in the middle here, there's this HTTP, right? We're going to the HTTP port, but we've got all of this TCP data that's going back and forth. Now you can see that we're acknowledging that this is HTTP. All that means is that Wireshark said, yep, you're using port 80 on this. So here are the actual sequence numbers that we're using along with this. Now these are the same examples that we did earlier, but I've included the sequence and acknowledgement numbers here. So these are the packets that are being referenced, right? Packet numbers and what's going on. So it's the SYN, SYNAC, ACK, and then an HTTP GET right here. Now this is where we're asking for data. So we'll take a look at the relative sequence numbers first. This is what we saw earlier, right? 0, 0, 1, and 1, 1. This is the relative sequence numbers, but the actual sequence numbers in hexadecimal were these values here. Now take a look at packet number 2, the sequence number that was used, right, ends in DDA0. The server comes back and says, yep, I got that, but I'm incrementing by 1 because this is the next thing that I expect from you. And sure enough, the client comes back with that sequence number. So the client now, right, so we do the SYN, SYNAC, ACK. Now it's up to the client to say, well, what did I want? Well, I wanted your web page. So that's why we see the source IP address 1.1, 1.1 2 times in a row. So it finished the handshake and then it said, all right, here's the business that I'd like to contract. So the sequence number is the same, but of course in this particular packet there will be data. So it'll be an HTTP GET. And so the amount of data that was sent was 405 bytes, meaning that the acknowledgement number will be incremented by 406 because it's the next thing that we expect. And so we can follow this through our conversations when we're dealing with TCP. You can also see these lengths here in the right-hand part of your screen. There you go. So that's an example of how the sequence numbers increment and how we acknowledge the data that's being sent. Now, window size is an important idea. It is TCP's flow control. It is how TCP handles congestion. So each side sends a window size during the handshake. Now, this can change over the course of a conversation, but it has a big impact on performance because we can adjust the window size. And so when a client says to a server, here's my window size, when the sender, the server in this case, sends data down, it keeps track of how big the client's window size is. And it goes, okay, I just sent the client 1,000 bytes. And if the client's window size was 10,000, the server now knows that the client can only handle 9,000 bytes more. If I send several more packets, then the window is decremented by however much data I've sent. The only thing that opens up the window again, the only thing that allows the server to send more data is whether or not the client has acknowledged the data that was received. So in actual operation, the server sends data, closing the client's window, but the client acknowledges data and that opens the window back up. If the window shuts down, then the server is no longer able to send any more data until an acknowledgement comes. Now, operation today, we have something called window scaling factor that creates enormous window sizes, so they almost never shut down. Now, conceptually, we call this sliding window because the window can be adjusted not only while we're sending data, but also over the course of a transmission, we can change the window size, right? If we're able to process the data and if the network is fast, we can change the window size. Conversely, if we're getting too much data, or if I'm dealing with a very, very slow network, then I can adjust the window size accordingly. So the graphic that I've included here is just shows how this window size behaves. Now, if a client is being overrun, I can tell the server to shut up by closing my window. And that's why we call it congestion control. That also clears up traffic that might be in the network because senders are told to be quiet by their clients. So if we go back to our packet, we now realize, oh my goodness, now I understand what the source and destination ports are because I have this concept of client-server architecture. I now understand what the sequence numbers and acknowledgement numbers are all about. I understand this flag field here, that I've got the SYN, ACK, and FIN flags, but there are others, reset flags, push flags. And then now I understand what this window size is all about. Now the user datagram protocol, also up there at layer 4, also at the transport layer, also handling some transport layer functions. It's RFC 768, but it's a very short RFC because UDP doesn't really want to do very much except give us this ability to do multiplexing of ports. So here we see the ASCII art. This is from the RFC, right? The source and destination ports. Here we see them in an actual UDP packet. This one happens to be TFTP. So it's just a packaging method that allows us a procedure for applications to send messages back and forth. We see UDP used in two places. One is anytime we got a short conversation. So any service-oriented protocol, DNS, DHCP, TFTP, these are short control conversations, or where we have streams of data where we don't want to be bothered with error recovery. We don't want to keep track of all that. You can sort of imagine the impact on a real-time conversation like a voice call or a video call if we were delaying to try to get data back that was lost. That would disrupt the call. So these are the two cases that we see UDP really shine. Now, previously we talked about DHCP. It's how we get our IP address. It's how we learn about a domain name system server. So what's the point of the domain name system? And why is it in this particular video? Well, DNS is part of almost everything that we do on the web. You can get away with specifying web pages via IP addresses, but we don't do that because we don't know them. So almost everything that we do requires a lookup first, a DNS lookup. Now, DNS is what we call the phone book of the internet because we don't know all of these IP addresses that are out there. They're hard to remember. It's much easier to remember names. So when you go to a website, the very first thing that you do, always, is you do a DNS lookup. So there's some server out there that has text files full of all of this information. So you go to a website, but the first thing that you do is you go to your DNS and you say, can you give me the IP address for this website or this URI? Now the web server has two basic forms of lookup that it does. If you say, here's this website, can you give me the IP address? That's what we call a forward lookup. If you do the opposite, then you say, I already know the IP address. What's the name of this thing? That's a reverse lookup. Now, DNS servers can store or cache results for recently completed queries. So there's a periodicity or a time associated with each lookup. And a server can hang on to this and say, look, you just asked me that already. I stored the information so I don't have to find out. Well, why would a server have to store that? Well, sometimes domain name system servers don't know the answers. So they have to ask a friend. So DNS is organized in what we call the namespace tree. And so your local DNS might be authoritative for everything in your company, but it doesn't know anything about the rest of the world. So when you ask questions that are going someplace else, right? So I'm an RIT. If I ask any question about Microsoft or Google or YouTube, then my local DNS has to ask the next DNS up the tree, and so on and so on and so on. These questions might go all the way to what we call the root servers or the root of the tree. Now, my name server can either say, look, I don't know, you figure it out, or it can say, well, I'll help you, and I will ask all of these servers the question. So again, when I go to a website, the first thing that happens is I got to find the IP address. So I ask DNS for that. My DNS server might do a recursive lookup, which means it's going to help me, and it's going to go all the way up the tree to find the answer, and eventually give me the IP address of the destination. And that's actually what I used to do my web page. Now, DNS is UDP port 53, so if you're capturing packets, don't be confused. You go to a web page and you'll see all that DNS stuff first. Now, the chapter also spends a little bit of time on URIs or Uniform Resource Identifiers. It's the proper name. Sometimes we say URLs, Uniform Resource Locator, but URI is the official name. And it is the formal name or the formal way to look up a network resource, especially things that are out on the web. So when you look at how you actually type it into the browser, you might actually type up www.searchskills.com, right? That might actually what you look for. But the thing that comes back might actually be the real pathway to it. And then out front, you'll see the https:// or http://. That is the scheme or the structure, but it's really the protocol. And this would, you'll see the TCP packets going to either port 80 or port 443. So the URL or the URI or the server's name is the www.searchskills.com, and then the path name on that server would include the slashes, right? In this case, blog. So it's not uncommon for you to go to a website and then that gets remapped to something that includes the pathway, and then the query that you make gives you the IP address for that resource. So what you're asking is, hey, here's this URI. Can I have the IP address? And you get back the IP address that's actually to a particular path, because it's not uncommon for web servers to have lots and lots of directory structures to give you the file that you are actually asking for. Now, HTTP, or the Hypertext Transfer Protocol, is how we get data, how we get files from a web server. If we're doing HTTPS, that's just secure, it's encrypted. And the very first message that we commonly use with HTTP is something called an HTTP GET. And you saw this referenced in the previous slide. So you're going to do DNS, UDP port 53, and then you're going to do HTTP port 80 or HTTPS port 443, where you actually ask for the data, and the browser, your web client, actually gives us the formatting for the data that comes down. So HTTP has its own way of organizing data. Okay, that's a lot of stuff. Let's do the do you know this already questions. Which of the following header fields identify which TCP/IP application gets data received by the computer? Choose two. Well, we know that in the client-server interaction, we're asking for the source and destination, IP addresses, source and destination, port numbers. But because this question had both TCP and UDP ports in there, there was no way to differentiate them, so those two are the correct answers. And this is the multiplexing that we get when we have data coming back to our computer. So D and E. Question number 2, which of the following are typical functions of TCP? Remember that we're talking about TCP here, not UDP, and TCP, that mother hen protocol, does all of these things: flow control, error recovery, multiplexing, ordered data transfer, right? Those sequence and acknowledgement numbers and the window size. Which of the following functions is performed by both TCP and UDP, right? So UDP doesn't have those advanced functions, but they both do that multiplexing using port numbers. Question number 4, what do you call data that includes the layer 4 protocol and data given to layer 4 by the upper layers, not including any headers and trailers from layers 1 through 3? Well, the language that we use at TCP is a segment, right? So you prepare a segment, and the sequence and acknowledgement numbers are all about the segments. And since we're talking about layer 4, it's a layer 4 protocol data unit, or PDU. In the URI example here, http://blog-certskills.com/configlabs, which part identifies the web server itself? Well, the answer that would come back from DNS would be the blog certskills.com. The rest of that is the path, and of course, HTTP is the protocol or scheme used. Question number 6, Fred, good old Fred, opens a web browser and connects to the certskills.com website. Which of the following are typically true of what happens between Fred's web browser, the web client, and the web server? Choose 2 answers. Well, because we're talking about HTTP traffic, we know that this is going to be port 80, and we know that this is going to be a TCP-based protocol. All right, remember that we're in volume 2, so we're back down at those low-numbered chapters. So the chapter 2 look ahead is going to be access control list, or ACLs, as sometimes folks say. So ACLs, there's a lot of different kinds of ACLs. Standard is our first type that we're going to tackle in Chapter 2. We'll go over the operation and how you build them. Now, don't forget that we're now done with Volume 1. So register your books. You get lots and lots of resources. You get practice questions and quizzes and things like that out there, in addition to the lovely videos I'm doing for you. Well, there were lots of ideas in this chapter, lots and lots, right? Client, server, TCP versus UDP, all the things that happen at layer 4, error control, sequence numbers, flow control, all of that stuff. So lots of things that we did on this chapter. And of course, we talked about DNS. So it's not lowercase s there, but there we go. DNS performs a really, really important function, which gives us those lookups. And DNS servers sometimes have to ask friends for help, and they will often do a recursive query for you to give you the answer that you need to get to the resource or the URI. Okay, like and subscribe to start a little security with ACLs in Chapter 2. And whether you're using TCP or UDP, may those packets always reach their destinations. And now we're doing volume 2. This is CCNA. You can do this.